Welcome to this explainer. So if you've been trying to build a PC or upgrade your setup lately, you've probably noticed something incredibly frustrating happening in the hardware market. Today, we're investigating the true culprit behind the disappearing consumer RAM and those delayed graphics cards that are currently plaguing the tech world. We're going straight to the source material to unpack the massive structural shift that's causing this whole crunch.
Where on earth did all the graphics cards and memory go? It is literally the exact question on every PC builder and gamer's mind right now. You look at the market, you see skyrocketing prices, bizarre scarcity, and you kind of have to wonder, is this just another supply chain hiccup? Or maybe artificial hoarding? But the truth is actually much more fascinating, and honestly, a lot more structural than a simple shipping delay.
The unexpected answer comes down to a prime suspect known as high bandwidth memory, or HBM for short. In just 3 years, this incredibly complex, highly profitable component has gone from being a super niche specialty part to the absolute dictator of global memory availability. It is actively swallowing up the manufacturing capacity of the entire tech ecosystem.
Okay, let's dive into this. Section 1. Meet the culprit. What exactly is HBM?
To really understand why your consumer RAM is disappearing, you first have to understand the absolute marvel of engineering that's replacing it on the factory floor. Think about the stark contrast here. Standard DDR5, the RAM that goes into your laptop or desktop, is basically a flat, two-dimensional sheet of chips laid out on a stick that you plug into your motherboard. HBM, on the other hand, is built like a massive 8, 12, or even 16-layer skyscraper. It stacks DRAM dies vertically right on top of a base logic die, creating an incredibly dense tower of memory that sits mere millimeters away from the GPU it feeds.
Now, to connect these microscopic skyscrapers, engineers use something called through-silicon vias, or TSVs. They quite literally drill thousands of microscopic vertical channels straight through the silicon to link all these stacked layers together. It's an extreme, highly delicate feat of engineering, but for modern computing, it is absolutely mandatory.
So why go through all that trouble? Bandwidth. Pure and simple. AI accelerators, like NVIDIA's H100 or AMD's MI300 series, they calculate math far faster than ordinary memory can feed them data. Without HBM, these massively expensive AI chips would just sit there idle, totally starved for data. By utilizing the skyscraper design, HBM delivers 5 to 10 times the bandwidth of the memory on a normal graphics card. Modern AI GPUs actually wrap about 8 of these massive HBM stacks right around their compute die just to keep the data flowing.
Section 2. The weapon. Why HBM eats wafers.
But here's where this marvel of engineering becomes a serious problem for everyday consumers. Let's transition to the factory floor and look at exactly why building these memory towers is causing a catastrophic bottleneck in the global supply chain. Simply put, HBM is brutally inefficient to manufacture. First, the dies themselves have to be made larger just to fit those microscopic TSV channels and the interface logic, which means fewer chips fit on a single silicon wafer. Second, the stacking process is incredibly difficult. A single defect anywhere in a 12-layer tower can ruin the entire stack. Talk about a high-stakes game of Jenga, right? All of this translates to low yields and massive inefficiency on the manufacturing line, directly consuming the wafers that would otherwise be used for standard memory.
And this brilliantly illustrates the true cost. 3 to 4. That is how many standard DDR5 wafers are sacrificed to create just one HBM equivalent. Let that sink in for a second. 1 bit of HBM consumes roughly 3 to 4 times the wafer area of 1 bit of standard DDR5. Every single time a manufacturer points a wafer towards HBM, they are actively removing 3 or 4 wafers worth of ordinary memory from the global market.
Section 3. The generational arms race.
Now, if this were a static technology, the market might eventually catch up, but it's not. We are in the middle of a relentless, annual generational arms race that guarantees fabs will keep dedicating more and more capacity to HBM. Look at this dizzying timeline. First, we started with the HBM3 era, delivering around 819 gigabytes per second. Then HBM3E became the 2026 workhorse, pushing past 1.18 terabytes per second. Now, HBM4 is ramping up through 2026 for NVIDIA's new Rubin platform, delivering jaw-dropping bandwidth north of 2.8 terabytes per second. And HBM4E, it's already slated for 2027 and 2028. Every single generation is faster, denser, more packaging-intensive, and dramatically more wafer-hungry. The screws on everyday consumer supply are quite literally just getting tighter.
Now, what's really interesting about this is Section 4, the motive, following the AI money.
To understand why companies are so willing to sacrifice consumer RAM, we just have to follow the irresistible economics driving manufacturer decisions. The price difference here is absolutely staggering. A cheap commodity DDR5 memory stick runs for about $5. Compare that to HBM. An HBM3 stack commands around $200. HBM3E goes for about $300. In fact, suppliers pushed prices up roughly 20% for 2026, which is almost unheard of for a maturing product. And the new HBM4? An estimated $500 per stack. When a fab looks at a piece of silicon, they see a choice: make a $5 commodity or build a $500 stack that AI companies are basically begging for. That poor $5 consumer stick never stood a chance against the data center giants.
The broader market numbers are even more wild. The total addressable market for HBM is projected to jump from $35 billion in 2025 to roughly $100 billion by 2028. That is an explosive 40% annual growth trajectory. To put that into perspective, in the memory industry, growth is historically in the low teens. So yeah, HBM is completely redefining the financial realities of semiconductor manufacturing.
Because of that explosive growth, nearly half of all DRAM revenue is now swallowed by HBM. It went from a mere 8% of DRAM revenue in 2023 to a projected 41% in 2026. Almost half your money is coming from one single product. When that happens, the DDR5 in your laptop or the chips in your phone simply become an afterthought. They're just something the fabs make with leftover spare capacity.
Section 5. The Turf War, a three-horse fab race. With that much money on the table, it's no surprise that the competitive landscape has shifted into hyperdrive. 3 of the planet's largest manufacturers have entirely reorganized themselves to fight for this booming market. This is a fierce, high-stakes battle for absolute dominance. For a long time, SK Hynix led the pack, holding 50 to 62% of the market, with 90% of its supply going directly to NVIDIA. But now, Samsung has mounted a massive comeback, passing NVIDIA's HBM4 qualification to supply the Rubin platform. Meanwhile, Micron has completely sold out its entire 2026 HBM capacity. As of mid-2026, all 3 of these heavyweights are officially qualified and in production for NVIDIA's latest generation. The battle has really shifted from who can even build this to who can offer the best yield and price.
Let's move to Section 6 and see how this builds out. The fallout, collateral damage to your GPU.
Because this massive turf war and manufacturing shift, it doesn't just stay in the data center. It directly hits the hardware that we actually want to buy. Here is the cruelest twist for gamers and PC builders simply trying to put together a decent rig. Suppliers are so focused on prioritizing data center HBM wafers that the specialized GDDR7 memory used in consumer graphics cards has gone critically short. Because of this, NVIDIA reportedly had to cut their RTX 50 series production by 30 to 40% in the first half of 2026. The wafer squeeze didn't stay in its lane. It's actively thinning the supply of the exact consumer GPUs you would buy to run AI locally.
Section 7. The structural fragility.
So, where does this leave us? Let's conclude our investigation by taking a step back and assessing the broader, honestly somewhat unsettling reality of a tech ecosystem that has become entirely dependent on a single bottleneck. It'd be easy to point fingers and claim this is artificial scarcity, but it's not. Actually, scratch that. There is no villain hoarding chips in a secret warehouse. AI genuinely is bandwidth bound, HBM legitimately is the solution, and the manufacturing process really is this inefficient. What we have here is a structural discomfort. A wildly profitable component naturally commands the market's attention, and a rational manufacturing sector feeds its most profitable customer first. Simple as that.
This quote from the source material perfectly summarizes the state of the industry right now. The tower in the data center is eating the fab, and everything else in computing is standing in its shadow. Consumer hardware, smartphones, standard memory, they have all been completely eclipsed by the massive, insatiable demands of data center AI.
Which leaves us with this final, incredibly pressing question. Will the intense competition between SK Hynix, Samsung, and Micron finally inject enough supply to bring the market back into balance? Or is this hyper-concentrated AI edifice dangerously fragile? Think about it. If AI demand ever corrects, this exact component is where the overbuild and the pain would land first. It's a pretty precarious future for the broader semiconductor economy, and definitely something to think about before you plan your next PC build. Thanks for joining this explainer, and stay curious.